Okay, what's the biggest number you can even think of? A billion? A trillion? What if I told you there's a kind of math that makes numbers so ridiculously huge they make a Googleplex look like pocket change? Well, today we're diving into the absolutely mind-bending world of tetration.
You actually already know this pattern, you just might not think about it. Right? Multiplication is just adding over and over again. Exponents are just multiplying over and over again. So, what happens when you repeat exponents? You get something that looks, well, a little weird.
You might see something like this. This is called Knuth's up arrow notation, which is a whole other rabbit hole. But for now, what on earth does 2 double arrow 4 even mean?
It means this: a power tower. 4 2s stacked right on top of each other. A tower of pure exponents. But how in the world do you even start solving a thing like that?
Okay, here is the absolute most important rule. You start from the top, always. So the very first thing we do isn't 2 squared at the bottom, it's that 2 squared way up at the top. So that becomes a 4.
So now our little tower is a bit shorter, but look what we have already. 2 to the power of 16. That's a pretty big number, but honestly, it's nothing. The final answer is
65,536, just from 4 little 2s. This, my friends, is the incredible power of tetration. And trust me, we are just warming up.
So let's break it down. What is tetration really? The best way to think about it is as the next logical step, the next rung on a ladder of math operations.
See, each operation is just a souped-up version of the one before it. Multiplication, that's just doing addition again and again. Exponentiation, that's just doing multiplication again and again. So tetration is just what you get when you do exponentiation again and again. It's this beautiful, clean, logical step up.
And the name itself is pretty cool, right? Reuben Goodstein came up with it back in '47. It literally means the fourth operation, after addition, multiplication, and exponentiation. Sometimes it's called Hyper 4, which honestly sounds like something straight out of science fiction. And as we're about to see, the numbers it spits out are just as wild.
Okay, so we know what it is, but how do we actually calculate these things? Well, like we saw with our first example, there is one golden rule, one rule you absolutely cannot break.
This is the law of the land for power towers. You have to work from the top down, or if you write it out, from right to left. You solve that topmost piece first, and then that answer becomes the new exponent for the number below it, and you just work your way down to the base. And oh boy, does the order matter. Just look at this. This shows you why that rule is so incredibly important. If you calculate our first example the wrong way, from the bottom up, you get 256, which, is a fine number. But if you do it the right way, top down, you get 65,536. The difference is gigantic. So remember, always start at the top.
All right, we know the rules. Let's really crank things up a notch. We saw what 4 2s can do. What happens if we just nudge that base number up by 1? Let's see what 3 double arrow 4 looks like.
So we start at the top, just like we're supposed to. 3 to the power of 3 is 27. Simple enough, right? So our new power tower is 3 to the power of 3 to the power of 27. Now, for the next step, we've got to figure out what 3 to the power of 27 is.
And wow, just like that, we're at a number over 7.6 trillion. I mean, to put that into perspective, that's more than the number of stars in our entire Milky Way galaxy. And remember, that's not the answer. That's just the new exponent we have to use.
Just look at this insane growth. This right here is the entire point of tetration. It's a way to write down numbers that are just fundamentally beyond our comprehension. The third tetration of 3 is already a number in the trillions, but the fourth, it's a number so huge that if you tried to write it down, it would have over 3.6 trillion digits. It is physically impossible to write that number down in our universe.
Okay, so you might be thinking, that's cool, but what's the point? Numbers this big feel like they're just an abstract curiosity. But tetration isn't just a party trick. It actually has real-world applications in some pretty advanced fields.
In computer science, for example, it pops up when you're talking about the complexity of certain algorithms. It helps us understand just how much brain power a computer needs for a problem that grows insanely fast. It also shows up in number theory and even in modeling super complex systems like population growth or even chaotic weather patterns.
And if you can believe it, this ladder doesn't even stop at tetration. You can keep going. The next step up is called pentation, which is repeated tetration. Then you've got hexation, and it just keeps going, an infinite chain of these so-called hyperoperations.
But even just sticking with tetration, there are still some really deep mysteries that have stumped mathematicians for a long time. These operations grow so fast, they create some incredibly tricky and fascinating questions.
So I'll leave you with this final thought. What if you take a number like pi, an irrational number that goes on forever, and you tetrated it, pi to the power of pi to the power of pi to the power of pi? Could that unbelievably complex number somehow magically boil down to a simple, perfect whole number like 5 or 100? The incredible answer is nobody knows. It's one of the great open questions in this strange world of huge numbers. And it's a perfect reminder that even in math, there are still vast, uncharted territories just waiting for us to explore.